Okay, thanks, Jean-Pierre. And hi, everybody. Please feel free to stop me at any moment and let's have some discussions. I'm gonna talk about an introduction to density functional theory, but maybe a better title for this talk would be an introduction to band structure calculations in general, and what are the sort of computational techniques that we use to do these calculations. My talk is going to be kind of a continuation to maybe solid state 1, something like that, a course that you had already, and hopefully we'll build on that. So I start with what we all learned from Ashcroft and Merman, the nearly free electron approximation. The goal in materials computations is really to solve the Schrodinger equation for a system of many electrons. And you want to get the solution to the Schrodinger equation for all the block electrons in a periodic potential. So here every dot is an atom. This is what you learn in your solid state course. The dashed line here, they are single atomic potentials. These are potentials of single atom. If you have just a linear array of these atoms, then the solid lines here, they show you the periodic potential of those. And if you have planes of atoms, let's say this is one plane, then you have another plane on top, and then another plane on top and below, then you get this kind of modulated periodic potential that you have inside solids. That's going to be the U of R. And we all learned from Bloch's theorem that this U of R is periodic with the periodicity of the Bravais lattice. And as a result, the Bloch theorem tells you that the solution to the Schrodinger equation will also be periodic with the periodicity of the Bravais lattice. So what we learned from Ashcroft and Merman is that you can write this wave function as a sum over plane waves. The plane waves are summed over these capital K, which shows the reciprocal lattice vectors, the Fourier transform of the real space lattice. And you do this because you're in the nearly free electron approximation. So the free electron is given by a plane wave. You sum over plane waves over the entire reciprocal lattice, and you get your wave function. But then what you can do is that you can then write the Schrodinger equation in momentum space. Now here it's written in real space. You can Fourier transform it to momentum space. And these C coefficients, these become in fact a part of the Fourier transform of your Schrodinger equation. And then you can, for example, introduce a band velocity, a velocity that's given by a gradient of the energy as a function of momentum. And this energy as a function of momentum is what we call the band structure, the energy of electrons given as a function of their momentum. So that would be our band structure. In the nearly free electron approximation, what we learned, again from sort of Ashcroft and Merman, is that more or less a quadratic dispersion explains the behavior of electrons. When your electrons are simply a sum over a bunch of plane waves, then you would expect that the energy would go as h bar squared k squared over 2m. So it's quadratic with energy, and that's what you see here. See, this is a quadratic band dispersion. And here is another quadratic band dispersion that's going to go up here and curve, downward curvature, upward curvature. We learned that the curvature of the bands will give you the effective mass. So the second derivative of the energy will give you the 1 over effective mass. The first derivative will give you the velocity of electrons. And the other thing that we learned in the nearly free electron approximation was that the main effect of having a periodic potential is to open a gap at the so-called Bragg planes. What Bragg planes are, they are shown here as half K. They are bisectors of the reciprocal lattice vectors. This is the formal definition of Bragg planes. They are the bisectors of the reciprocal lattice vectors. Okay, so and at those points, the effect of U, which is here in the in your Schrodinger equation, is to open a gap. In fact, if you do not open a gap at the Bragg planes, then you have something very, very special. That's actually the start of topological materials. If this degeneracy is protected and you cannot open it by a simple nearly free electron approximation, then you have a very special material. But usually this is what happens. Okay, now the goal of our sort of lecture here is to understand how we can compute the band structure, or how we can solve the Schrödinger equation, not for just a nearly free electron system, but for a system of electrons that interact with each other. We usually work in an approximation that is called independent electron approximation. It means that you assume that electrons do not interact directly with each other, but of course there is some interaction between electrons. The interaction is not just a direct electron-electron interaction. The interaction, you can encode it in this potential, in the U that used to be only the periodic potential of your lattice. Now you can encode the interaction between electrons into this U, and this is what we call an independent electron approximation. You still assume that electrons do not interact directly, but of course the effect of that interaction is encoded in this U. The final goal, again, is to find the wave function. And when you find the wave function, what's the use of that? The wave function is, in fact, a map of the electron density. That's what you get. You get the landscape of charge distribution inside your material, you know, where electrons live. And where electrons live is that electrons live in the bonds between the atoms. For example, this is a crystal structure of titanium carbide, and here is a titanium atom, here is a carbon atom, and you can see the mapping of the electron density. It is nothing but a mapping of this function, psi squared times charge of electron. That would be, the psi squared is the probability of finding the electron. If you multiply it by charge of electron, you get the distribution of electrons, electric charge, inside your unit cell. Okay, now how do you go about and do that calculation? So usually, in order to do this calculation or in this computation, we use a iterative approach, and the approach goes as follows. We really, to start, we don't know exactly how electrons interact with each other. Of course, there's some Coulomb potential between electrons, but we don't know at any given time where electrons live, because you have to first solve the Schrödinger equation, and you have not yet solved it. Okay, so what you do is that usually, in order to know this potential, you have to know two things. You have to know the periodic potential of the lattice, which you know from the lattice structure. But you also, as I mentioned in the previous slide, you have to also have some understanding of the effective interaction between electrons, which can be also periodic and which can be encoded in U, but you don't know that until you calculate psi, until you know what's the charge distribution inside the material. So you have a problem of twofold. You don't know psi, and you don't know U, and then you need each of them to calculate the other one. Okay, so how do you go about solving that problem? What you do is that you often start with a guess, some guess as to what would be your U, and you call that a U0. So you start with some shrewd guess of the potential, and there are various schemes to come up with that guess, but you start with some guess of U0. That would be the 0th order calculation, and then you solve the Schrödinger equation and you get the 0th order solution, which is psi of k of r of 0. Then what you can do is that you use this psi k of 0, and you can plug it back into you can go back here and construct a map of your electron density. And by knowing the electron density, now you know at any given moment of time, you know where the electrons are, and you know what's the charge distribution of electrons. So you can actually compute the electronic part of U, which you didn't know until you get this psi 0, right? So now you can compute this new U, knowing, having a 0th order wave function. And then this becomes your U1. Now U1 contains the periodic potential of the lattice plus the guess that you had originally from where electrons can be. You solve the Schrödinger equation. You have now a wave function. You recompute the charge distribution, and then you recompute your potential, and this is what you call U1. Now after this, you do a test of convergence in your problem. And the test of convergence, usually, there are many criteria that you can check, but there are usually two criteria that are important. One is a charge criterion, and the other one is an energy criterion. The charge criterion, simply what you do is that you calculate E psi n plus 1 squared. So let's say here you calculate say the first solution versus the 0th solution, for example. And you see in every iteration that you're doing in your, say, in your computer, you see that in every iteration, how much does the charge distribution change? Let's say in step n plus 1 compared to step n. And then you have to have some kind of, you set some criterion. For example, you demand from the computer that if the changes in my charge distribution at every position, for example, here is my charge distribution, at every position, if the change in charge distribution is, let's say, less than 0.01 coulomb, I give it a pass and I stop my computation. If not, I will reiterate my computations. So this would be a test of convergence on your charge distribution. The second test of convergence is on energy. In energy, what you can do is that you compute your potential at every step and you compare with the potential in the previous step. And again, you have to set some criterion. For example, you say if the change of potential is less than, let's say, 0.001 Rydberg, and typically in these computations we use atomic units. For energy we use Rydberg, which is the binding energy of a hydrogen atom, 13.6 electron volts. For distances, usually we use the Bohr radius as the unit of distance, which is half an angstrom. So the computations are always done in atomic units. Now, okay, so then for energy, you would ask again, how does my convergence look like? At every iteration, I compare my potential to the previous iteration, and if it's below a certain threshold, then I give it a pass. And if both criteria converge, you give it a pass and you're done, even after the first iteration. And sometimes it happens that in the first iteration, you get everything right. But that's very rare. Usually that doesn't happen. So if your computation does not pass the convergence criterion, then you go to the next step. And what you do is that you use the potential, for example, U1, you use that potential and you recalculate a new wave function. And from that new wave function, you go back and you recalculate your electrostatic potential, and you get a new U, and you put in the new U and the new wave function in your convergence criteria and check it. And if it passes, you're done. If it doesn't pass, you go through the next iteration. And you go so on and so forth until you satisfy both convergence criteria, and at that point you cut the computations. It's an iterative process, and of course you have to have some criterion, because otherwise you can go on forever. It's the job of you to sort of decide where you're going to cut the computation, and then it's again your job to decide whether the results are meaningful or not. So this is maybe the first thing I want to say about all these DFT computations, is that you have to really take them with a grain of salt. The methodologies are correct, the computations are correct, you're solving iteratively an equation, but the end result usually starts with a guess, and that guess can really determine, it can set the course of the outcome of the computation. And it can happen that if your guess from the beginning was really far from the reality, then you could end up in a completely wrong place. So DFT results are interesting and typically included in many publications, especially by material experts, but we all know that they have to be taken really with a grain of salt, and you cannot always just take them as a given. Okay. Now here I show an example of the problem, for example. So this is just a DFT calculation, density functional theory calculation on vanadium. It's just the element. You would think this is very simple, right? And it's a BCC lattice. So here is the Brillouin zone of a BCC lattice, and you typically plot the energy as a function of momentum along certain paths. We call them the K path. So you start from, let's say, 0.000 at the center of the Brillouin zone. It's called gamma. Then you plot it, say, along this gamma to n, where n is the center of this square face right here. And each of these points have a name, as you've seen probably in your solid state, they have a name. And again, mind you that this is the first Brillouin zone of a BCC lattice. The first Brillouin zone is also called a Wigner-Site Cell. And what it is that it's actually these planes that you see here, they are Bragg planes. They're all bisectors of a in the reciprocal space, you take a lattice point, you connect it to the nearest neighbor lattice point, and you draw the bisector plane that cuts this path in half, and you draw this over all the reciprocal vectors. And then you look at the volume that is generated amidst all these bisector planes. That is called the Wigner-Site Cell, and that is your Brillouin zone. That's your first Brillouin zone. So you go along a path in there, and you start calculating energy as a function of momentum, and you draw it. This is the band structure. Now, this is calculated for vanadium in from two different starting points. Vanadium has 5 electrons in its valence shell. You can start from, let's say, 3d3, 4s2, or you can start from 3d4, 4s1. And that means that your starting potential will be different between these two cases. Simply, you arrange electrons differently between D shells and S shells. And if you do the calculations, you see that overall they look the same. Let's say look at this kind of distinct feature right here in the middle. You have the same thing here, right? And the splitting over here, you have kind of the same thing here. The splitting here, you have almost the same thing here. So overall, they look similar, but the actual energies are quite different between these two calculations for the same element. This is just an element, right? And then you have to pick which one is correct and which one is not correct. And you can imagine that if you go beyond elements, just your starting point can take you to very, very, very different solutions. So, okay. Now, what we are interested, again, another thing that I want to say is that the DFT computations, they are specifically good to calculate the band structure of metals, specifically. It's better when you work with metals. And in metals, what you have is that you have a nucleus, you have core electrons, and you have valence electrons. Valence electrons are electrons in the outer shell. Those are the electrons that participate in metallic bonds. For example, in vanadium, it would be the 4s and 3d electrons. And sometimes even the 3d may not participate so much in metallic bonding. The core electrons are anything that is too close to the nucleus and too localized around every lattice point. So those are called the core states, and the core states stay near the nuclei at every Bravais lattice site. Now, again, in solid state 1, you learn the tight binding approximation. Tight binding approximation is a very good method to understand where the core electrons are. The method is based on having, say, this is your lattice. Every blue circle here shows your nucleus. And every wiggle here shows an atomic wave function. And what you do in the tight binding approximation is that you put atomic wave functions at every Bravais lattice site, and then you look at the overlap between the atomic wave functions in between the Bravais lattice sites. And usually these overlaps for the core electrons are small, because the core electrons are too close to the nuclei, and they do not overlap that much in the space between the neighboring atoms. And that space, we call it an interstitial. So we have an interstitial space, which is, say, here in the middle, and then we have a core region, which is here, where the core electrons live. In tight binding approximation, you learn that you can write the wave function of, this is the solution to the lattice Schrödinger equation. You can write it as a sum over these atomic wave functions multiplied by a plane wave. And here, conceptually, what it means is that you write your atomic wave functions as given here, but then you modulate them by some plane wave construction, some e to the ik dot r. And what happens is that you see that the amplitude here is modulated by the e to the ik dot r. So not only you have your core levels and atomic wave functions, but also you have some modulation that represents the plane wave-like behavior of electrons as they're going through the interstitials. Another thing that we also learned is that these atomic wave functions are not necessarily orthogonal to each other, so we make them orthogonal, and when we make a set of atomic-like orbitals that are orthogonal and they're a complete set, we call them Wannier functions. The Wannier functions are really, they look like atomic orbitals, but they're not exactly atomic orbitals. They're a complete and orthogonal set. So this was what we learned from the tight binding approximation. You can calculate the energy, the band structure from tight binding approximation. Usually the band structure energy here is calculated for the s orbitals. It is very close to the atomic s orbital energy, but it is modulated by these overlap integrals, beta, gamma, and alpha. And they're all given by some, for example, beta is an overlap between the wave function and the local, the lattice potential, the local lattice potential, the U. Or for example, alpha is an overlap only between the two neighboring wave functions. And gamma has a little more complex structure. It is a wave function, delta U, and the wave function on the neighboring lattice site. So these overlap integrals, they eventually come in and determine what is the band structure. So in the tight binding approximation, we use this local approach to compute the band structure of electrons. However, tight binding approximation is good, but it is predominantly based on core electrons. It's very successful when you're looking at core electrons, but when you go to valence electrons, it becomes more difficult. Tight binding may not be so successful because these valence electrons are going everywhere. They're not localized wave functions to begin with, so you have to deal with that. Okay, so here is a kind of a simple argument again to show why the nearly free, so we started from the nearly free electron approach, and then we looked at the tight binding approximation, but again, you want your electrons to have anyway some kind of free electron-like behavior, but this nearly free electron approach definitely fails. Not only tight binding is not going to work very well, but even your nearly free electron approach will not work well, simply because the nearly free electron approach was based on a perturbation theory that assumes that the lattice potential is not very strong. However, if you compute the lattice potentials, for example, you just write the lattice potential as a Fourier transform. This is U in K. This is the K space potential that goes into the Schrödinger equation. It is a Fourier transform of the real space potential, and you can do a very simple calculation. You just put in the Coulomb potential and take its Fourier transform. It will go as something like this. It will be ZE squared divided by K squared. And if you just rearrange this by multiplying by the unit cell size, which is A0, you get something that's proportional to E squared over 2A0. And E squared over 2A0 is the Rydberg. It's of the order of tens of electron volts. So even even in the simplest kind of estimation, you can see that these potentials are pretty large. Actually, they're of the order of tens of electron volts, and your perturbation theory is not really valid. Although nearly free electron approximation works really well at the end of the day, but it's almost miraculous that we can use a nearly free electron approximation and explain the behavior of metals. Toward the end of my talk, we will see the reasons why that happens actually. Why? Okay. Right. So one thing I want to say here is that the goal is to understand how you can construct valence bands. Okay, so how you can, so this is the nucleus, these are the core electrons, and these are the valence electrons. And we know what to do with core electrons. We do tight binding approximation. Okay, so here is the core levels, and you can modulate them by some plane wave. But then you want to understand how the valence electrons behave. And roughly speaking, the valence electrons have a stronger contribution from the plane wave. So here I'm showing the valence electrons. So this is the psi k of V valence. This is C for core electrons. For core electrons, more or less, you have these localized wave function. But for valence electrons, you have to have something that looks more like plane wave. But anytime that you approach the core region of an atom, so anytime that you approach near to the nucleus of an atom, you must get these oscillatory behavior of atomic wave functions. And why atomic wave functions oscillate? Because as you put an electron inside an atom, as you learn from quantum mechanics, you sort of confine electrons to a small space, and what happens is that due to uncertainty principle, the electron wave function starts to gain kinetic energy, and kinetic energy in the wave function of electrons means a lot of wiggles. The more the electron goes, the electronic wave function fluctuates, the higher the kinetic energy of the electron will be. So what you expect something like this. You expect something that looks like, you expect your valence states, the valence electron states, to be free electron-like in the interstitial region between atoms. But when you hit the atoms, you expect it to oscillate. That shows that there is a large kinetic energy because it actually enters a region of large potential energy, in fact. And so the electron sort of starts to wiggle. But also the wiggles of these valence electrons, they cannot be exactly the same as the wiggles of the atomic orbitals, because these are not atomic. This is a valence electron, it's not a core electron, right? And the valence wave function must be different from the core wave function. And again, we're going to see that one of the important things in DFT calculations is to tell you actually how these electrons wiggle when they get into the core region. And we're going to see how we can construct that behavior. But in a very simple sense, what you want to have is that you want to have your valence wave function to be orthogonal to your core wave function so that they don't mix. And when you make them orthogonal to each other, that means that you set an equation like this. You demand that the integral of say psi c star psi v would be 0. That means that the two wave functions are orthogonal to each other. And that ensures that the oscillatory pattern of the valence electrons would be different from the oscillatory pattern of the core electrons. In fact, the two oscillatory patterns are orthogonal to each other. Okay. All right. Now, this is the general concept in computing the band structures. You have to really kind of neatly tie together your electrons. You have to know what are the core levels. In order to know the core levels, you have to know the atomic potentials and the atomic orbitals very well. Then you have to, after that, once you have your core levels figured out, then you have to understand how you can construct your valence electrons. You know your valence electrons must have more or less a nearly free electron behavior, so more or less they should be some kind of plane wave, but they have to be, when they hit the core region, they have to be modulated by the core levels, and then you have to get the oscillations of electrons within the core region properly through the orthogonality condition that I showed. So all of this has to happen in your computation, and it has to happen correctly. Now, it's not an easy task. There are several approaches to do this, and we're going to go through these approaches. I will not talk about the pseudo potential, but I may say a little about it. But the first three, especially, I think are very pedagogically good to know. Cellular method, augmented plane waves, and orthogonal plane waves. And you see, I'm pretty sure you've seen this, a lot of you, in various papers. So we're going to sort of try and dissect these methods. So the cellular method. The cellular method was the first approach to calculate the band structure of sodium. It was implemented by Wigner and Seitz, the Wigner-Site unit cell. These two guys actually, they came up with the approach, the cellular approach. And the approach is fairly simple. So the idea is that you want to construct the solutions to the crystal Schrodinger equation, but those solutions should satisfy the block condition, which means that they have to be periodic in the Brevet lattice. So psi r plus capital R should be e to the ik dot capital R times psi of r. All right. So in order to get these solutions, Wigner and Seitz, they said that, well, because your lattice is periodic, it is enough for you to calculate or to solve the Schrodinger equation in one unit cell. And let's call it C0. And if you solve it in one unit cell, then you can just implement the block criterion or the block condition and kind of reproduce the entire periodic lattice, the entire periodic electronic structure. Okay, so the first thing you do is that you choose a unit cell, let's call it U0, C0, and it's chosen as C0 because it is typically chosen as the unit cell that is at the origin of your say reciprocal space. In fact, this has to be capital K, not capital R, but it's okay. So you want to choose a unit cell that is whose origin is at the origin of the space. It makes things much simpler. Okay, then the next thing that you have to do in the cellular method is that, so you choose one unit cell. Let's say you put the origin at the origin of that unit cell. Then you have to have boundary conditions. And remember, what we're trying to do is that we're trying to calculate the energy of valence electrons as a function of momentum. And these energies have to have quantized values. Your K space is quantized, your energies must be quantized. And this quantization, or the actual values of k's and e's, they always come from boundary condition. Again, from, say, atomic physics, we all learned this in quantum physics. When you write the Schrödinger equation for an atom, the thing that quantizes the energy levels of an atom is not just the Schrödinger equation. It's the boundary conditions. It's the condition that you impose on solutions on the Schrödinger equation. You ask the solutions to go to 0 when r goes to infinity. So you always ask an exponential truncation of the wave function for an atom, because an atom is limited in space, right? This boundary condition will give you a quantization of energies. This boundary condition will give you the quantum numbers n, l, and m, in fact. Same thing with the cellular method, except that in the cellular method, your boundary conditions are not on an individual atom, they're on the surface of a unit cell. And there are two boundary conditions that are demanded. The first one is a boundary condition on the wave function itself. And this is simply nothing but a restatement of the Bloch theorem. Okay, so you ask your wave function to be periodic. So when your wave function enters from a neighboring unit cell into this unit cell, you ask the wave function to satisfy this Bloch condition. The next condition is similar to the Bloch condition, but is applied to the gradient of the wave function. So you ask, essentially your boundary conditions are the following. First, you ask your wave function to be continuous as it crosses the unit cell from the neighboring unit cell. The second boundary condition is that you ask the gradient of the wave function to also be continuous as it crosses the boundary of your unit cell. Okay, and the negative sign here is simply because you define n hat is the direction is the normal to the surface of the unit cell, and the normal to the surface of each unit cell always by default it points outwards from the unit cell. So the normal to the surface of the neighboring unit cell, which is here, will point inward for this unit cell. So there will be always a minus sign there. Okay, so that's just the layout of the problem. Then in order to do the cellular method, they had to, Wigner and Site, they had to do two approximations. The first approximation was as follows. The first approximation that you do in the cellular method is that you have, say, a real potential, and oftentimes the real potential looks something like this. It's large when it's dark. The dark blue means large potential. Light blue means small potential. So you have a large potential at the center where your atom is, and it kind of starts dying away in maybe an s orbital or p orbital or d orbital or whatever orbital form that you have. But also you have atoms in the neighboring unit cells, and therefore you have some interference between the potential of neighboring unit cell atoms and the atom in this unit cell, right? But the approximation, the first approximation that Wigner and Site did was to completely forget about this picture. They said, well, we don't care about this. What we do is that we simply approximate the real potential with a potential within the unit cell that is completely spherically symmetric. So they didn't care about the detailed structure of U. They said the only thing we demand here is that the potential would be spherically symmetric. It always starts maximum at the center of the unit cell and dies away within the as you move toward the margins of the unit cell. The reason why they did this is that, so they had to do, I mean, the computations were not very strong at their time, so they had to do a lot of things by hand. And the reason why they used this approximation was because they knew how to solve the Schrödinger equation in spherical coordinates, as you also have seen in quantum mechanics, right? So you know how to solve this equation. The solutions to this will be always a power law, r to the power of L times an exponential, e to the minus r divided by some reduced radius, multiplied by the associated Laguerre functions that give you the oscillatory form of the wave functions, right? And then when you impose the boundary condition, you quantize the result. That's how you get the hydrogen atom structure, and that's how you get the orbitals. Okay, they knew how to solve that problem. So essentially, they forced the unit cell to look like an atom. And then they said, okay, now we know how to solve this. We will solve it. So the problem became a kind of a radial Schrödinger equation. That was the first approximation. The second approximation that they had to do was a little bit more subtle. It had to do with the boundary conditions. So once they solve this radial equation, they get a set of radial wave function. These radial wave function, they are indexed by orbital angular momentum, because there is an orbital angular momentum in any spherically symmetric potential. There will be an orbital angular momentum. And now that you have this orbital radial wave function, you have to add also a spherical harmonic to it to construct the angular part of the wave function, which you can assume like a free, just a free electron approximation for the radial behavior of electrons within a unit cell. And then what you do is that now you sum a number of these wave functions in order to construct the real valence band wave function, which is the solution to the Schrodinger equation, the crystal Schrodinger equation. So what you do is that you have to essentially add a bunch of these terms together with some coefficient, let's call it A, and you sum them up and you can construct a wave function. But here's where the approximation comes. If you want to do a good job, you have to sum over a large number of these wave functions, as many as your solution gives you. For example, if your solution gives you, say, 10 wave functions, you have to sum over all your wave functions. But they assumed that you can sum over a limited number of these wave functions. For example, this A can be maybe only 2 terms, so you can have, say, A1 and A2, and you have only 2 terms to sum up and build a wave function. But in order to do that, you also have to reduce your boundary conditions. Essentially, the number of terms in the sum here should equal to the number of boundary conditions that you have. Only then you can construct what we call a secular equation, which is the way that you impose boundary conditions is always like this, that you have a number of solutions and you have a number of boundary equations. And it always gives you an n by n matrix equation. You diagonalize that matrix equation, you get the eigenvalues, right? This is called the secular equation. Again, a lot of it you've seen in let's say, quantum 2, even in undergraduate, probably when you have been solving the problem of, say, hydrogen atom. So the problem is very similar to the hydrogen atom. So this was their second approximation. And by these 2 approximations, they could solve the band structure of sodium. That was their goal. This was in 30s, right? So in all of these methods that I'm going to talk about, cellular method or any other method, there are really 2 things that determine the computational expense of any band structure calculation. The first one is the dimension of this secular or characteristic equation. How many terms do you decide to include in the sum, and how many boundary conditions do you impose on the unit, on the wave function? Of course, the more the better, but the more you increase, as you increase the number of terms and boundary conditions, you will increase the computational cost of your problem. The second thing is the size of the K-mesh. So here inside this Brillouin zone, you have a number of K points, and you have to plot the band structure as a function of K. And then you can determine how finely you want to chop your Brillouin zone. If you want to chop it into, say, 1,000 K values, then you have to calculate your wave function on 1,000 points. If you have 10,000 K values, then you have to solve your equation on 10,000 points, right? So these 2 factors determine the cost of any computation. And again, this is why the DFT calculations are never exact, because you have to cut it at some point. So even the best calculation by the best group from the best university in the world, it's always subjected to these problems, because you're always truncating the number of terms in the sum that gives rise to your band structure, and also you have to always do it on a limited K-mesh. Okay, so in the cellular approach, so for example, this is how Wigner-Site solved their problem back in the 30s. They really simplified the problem. What they did is that, first of all, they replaced the first Brillouin zone with a sphere. So this is the Brillouin zone. This is what Wigner-Site assumed to be their Brillouin zone. So they said, okay, what we do is that we just forget about this is too complex for us. We replace the FCC Brillouin zone of sodium by a sphere of the same volume. So you demand that, say, 4 pi over 3 R naught to the power of 3 equals the volume of this thing. Okay, so that's that. So why did they do this? Because this immediately reduces the number of surfaces and the number of boundary conditions. For example, here you have this hexagonal surface, you have this square surface, and you have this square surface on top and bottom and on the sides, right? But if you have a sphere, you only have one surface. You only have to deal with one surface, one boundary condition. In fact, you always have two boundary conditions, right? One for the wave function and one for its gradient. But here, because also they put the cell at r equals 0, this boundary condition becomes in fact trivial. So they only had to deal with this boundary condition, the boundary condition that has the gradient term in it. And because they had just a sphere, okay, the only thing that the boundary condition would give them was the following. The boundary condition turned out to be this. The derivative, the radial derivative of the wave function should go to 0. That means that the wave function should just smoothly cross a sphere. That's all. This is the way that wave function looks like. You see, it sort of wiggles. So here, this is 0. This is where the sodium atom lives. Okay, it wiggles here. This is within the core region. And then as it goes to the interstitial, which means near the surface of the Brillouin zone, it just levels off and becomes flat. The wave function becomes flat. And of course, the derivative of a flat function is 0. This is a cellular wave function. Now let us compare the wave function for this cellular method by the wave function of sodium s orbitals, the atomic wave function of sodium. If you have sodium atom and you don't care now about the lattice, this dashed line shows you the atomic 3s orbitals of sodium. Okay, remember that sodium has 3s1. The wiggles here are determined by the number of nodes in the radial or in the total wave function of your psi. And remember that the total number of nodes is n minus L minus 1. Here n is the principal quantum number, is 3. L is the s orbital, L is 0. And you do n minus L minus 1, you get 2. So you have to have 2 nodes. This is one of them, this is the second one. Yeah? So you go from plus to minus, one node, from minus to plus, the second node. And after that, this is the dashed line here is that atomic orbital. So first node, second node, and then remember that in the atomic Schrödinger equation, you ask the boundary condition to put the wave function to 0 as you get away from the nucleus, because of course the atom is limited to some radius, right? And this is the exponential decay of the atomic wave function. So now let's compare the atomic wave function of sodium with the wave function of sodium as a metal, the cellular wave function. If you're near the core region, the two wave functions are very similar, in fact. So at the center of every Brillouin zone where there is a sodium atom, the behavior of electrons is exactly similar to what they do in just atomic sodium. But as you get away from the core region and you enter the interstitials, then the two wave functions act very, very differently. The atomic wave function of sodium decays to 0, whereas the band structure of sodium metal keeps surviving, and in fact it becomes flat. And that's how the electrons keep traversing from one unit cell to the next unit cell, because this wave function becomes flat. So you can find these electrons with the same probability between neighboring unit cells. Okay. Now, this cellular method also was around the same time. This cellular method was really good, but it had problems with it. There are two problems with the cellular method. The first problem is that it is not easy to deal with boundary conditions on the surface of a Wigner-Site cell. So this is your unit cell. Remember that Wigner and Sites, they simplified this by approximating the unit cell with a sphere. But in general, this is your unit cell, and unit cells are often geometrically complex surfaces, and you have to impose boundary conditions on them. So this is of course difficult to do, and so it's a shortcoming of the cellular approach, because you have to deal with these boundary conditions. The second issue with the cellular method is that you always assume this spherically symmetric atomic potential, right? And the spherically symmetric atomic potential, in fact, poses a big problem. The problem is as follows. Let's say these are your atoms, and you assume this kind of potential. You see, this kind of potential. It's a spherically symmetric potential. It decays as you get away from the nucleus. Okay? So here is how it looks in a periodic structure. This is one atom. Your spherically symmetric wave function decays. But for the next atom, for the neighboring atoms, the same thing is happening. So these potentials and of course consequently the wave functions, they will intersect each other with a finite slope, in fact with opposite slopes. So as you traverse on this potential, if this is your wave function, for example, you come here, you hit a corner, and you have to go to the next line here. That means that the wave function itself is continuous, but the gradient of the wave function is not going to be continuous. It will change sign, right? Because you have these corners here. In fact, what you want to have is something that looks more like this red line. You want smooth potentials and smooth wave functions that are continuous between unit cells. Also, their derivatives are continuous between the unit cells. Okay, they're not pointy. Okay, so these two problems were problems of the approach, of the cellular approach, and therefore this was in late 30s and maybe early 40s that a new approximation was introduced known as Muffin Tin Potential, something that today also being used. It's probably the most successful approach, I would say, to at least DFT computations. The Muffin Tin Potential assumes a potential for the lattice that looks like a muffin tin. Which means that at every lattice site you have some kind of a potential well, but in the interstitials you have essentially flat potential. Your potential looks like this. You define some radius, let's call it R0. The R0 is, we call it the Muffin Tin Radius, and you will see this in any DFT paper. You will see this, the Muffin Tin Radius. The Muffin Tin Radius is simply the radius of that muffin tin here. So if the distance with respect to the center of the unit cell, for example, here is the center of this unit cell, and you're getting away from it. If you are within a muffin tin radius, you have an atomic potential. Okay, that is what you show as these wells in a muffin tin, or here it's shown by darker color. This is you can consider this as an atomic potential. This is what we also call it the core region, because core electrons definitely are always there. Anywhere beyond this distance, beyond the muffin tin radius, you approximate the potential to be constant, and in fact you may as well take it to be 0. So this is called the muffin tin potential. It looks like this. At the center, let's say this is zinc. Zinc has a hexagonal lattice, and where you are near the zinc nuclei or near the center of the unit cell, you have an atomic potential, and as you get away, you get 0. And of course, as a result, this looks like a muffin tin, and that's why they called it a muffin tin potential. The nice thing about this potential is that, of course, it solves the problem of discontinuous slope here. You see, the discontinuous slope problem of the cellular method will go away when you have this potential, because the muffin tin potential goes smoothly, goes to 0, it becomes flat, and then smoothly comes back up when you go to the next atom. Okay, so everything is very smooth here. Also, the potential itself, when you write it in a Schrodinger equation, yes?
Aren't the valence band levels supposed to be perpendicular to the core levels?
Yes, true. They should be, and we will see how we construct them. I have not yet got to that point. Yes, thank you. Very good. No, very good point. Yes, it's really the balance between the core and valence electrons is a very, very intricate balance, and I'll definitely show that. Okay, so the next thing is that if you assume that the potential is 0 beyond the muffin tin radius, then you can simply write your potential in a very compact form. It's a sum over all Bravais lattices of the atomic potential, which is finite as long as you're within the muffin tin radius, and it will be 0 as soon as you pass the muffin tin radius. Okay, now here, so this was the cellular method and an introduction of the muffin tin potential. What muffin tin potential did is that it gave rise to this other method. It kind of laid down a stage for the augmented plane wave method of calculating band structures, which we're gonna see now. Okay, so what is an augmented plane wave method? This method was invented by Slater. And the way that it works is that it assumes that the solution to the Schrodinger equation, to the lattice Schrodinger equation, is a superposition of a finite number of functions like this phi. These functions are called the augmented plane waves. And what are those? These functions, these augmented plane waves, have three conditions. First condition is that they are plane waves. These are functions that are plane waves in the interstitial region. So here I'm showing two neighboring unit cells. The dark orange is the Muffin Tin Radius, is the core region, and the light orange is the interstitial region. In the interstitial region, you see this is a very broad wave function reminiscent of the sinusoidal behavior of a plane wave. Okay, so in the interstitial region, every augmented plane wave must become simply a plane wave. The augmentation happens when you cross into the core region. So the second requirement is that the augmented plane wave has to be continuous as it crosses the boundary between the interstitial and the core level. So here I show in the interstitial region, I show it as a dotted line. It's the same function. I show it as a dotted line. It crosses into the core region, but it does not cross with an abrupt change of slope. It has to cross smoothly. Both the wave function and its derivative have to be smooth as they cross into the core region. The third property of the augmented plane wave is the reason why it's called augmented. When you get into the core region, okay, around every lattice point, then the augmented plane wave functions, they satisfy the atomic Schrödinger equation with an energy E, where this energy E as a function of K will eventually become your band structure. So here the augmented plane waves have a form that looks like an atomic core level, but it is not a core level. Just also going back to the question from our friend, this entire black curve is one wave function. It's phi k of epsilon. Okay, it's one wave function. That wave function has a wiggly form that looks like an atomic wave function in the core region, and it has a smooth form that looks like a plane wave in the interstitial region. So it's one wave function. This is for the valence electrons. Then we have the core electrons, right? So we have to add the core electrons to this picture. Let me see. Okay, I don't know where I get. Okay, before I get to the core electrons, all right. So within the core region, you want the augmented plane waves to satisfy exactly the Schrödinger equation for an atomic potential, for this V of R minus R, that it only exists within the core region, as we said before. Within the Muffin Tin Radius, it exists. So you do this, you solve this equation, you find, you write wave functions that can satisfy this equation within the Muffin Tin Radius. Beyond it, they become plane waves. And these wave functions, when you sum them over the entire reciprocal space, because they're functions of k, so you have to sum them over the k space, then they construct your valence band wave function. And that wave function looks like this. This is the valence band. So it is plane wave-like. It becomes wiggly, which is the atomic wave-like. And again, it becomes plane wave-like in the interstitial. And every time it approaches an atom, or every time it enters the Muffin Tin Radius, it becomes wiggly, like a core level or like an atomic level. And every time it goes back to the interstitial region, it follows the overall plane wave behavior that's shown here. Now, the wiggles of this wave function, although they are themselves atomic-like potential, atomic-like wave functions, these are not the core levels. The core levels have a similar shape, but they're actually orthogonal to the part of the wave function for the valence band that is inside the Muffin Tin Radius. Okay, we will see this a little bit in more detail in maybe one or two slides, few slides from here. All right. Now that you have these augmented plane waves, you want to from the augmented plane waves, you want to construct the valence bands. You have the valence bands and you have the core levels. The way that you construct the valence bands is just like in the cellular method. You have to sum the augmented plane waves over your reciprocal lattice. And again, there comes a choice of any computations as to how many of these wave functions do you include in this sum. If you include, say, an Avogadro number of wave functions, you get an exact solution, right? But this is impossible. Computationally, you cannot afford it. As a result, you always end up having usually about 100-ish of these wave functions that you knit together or you put in this sum, and you get an approximation to the Schrodinger equation, the solution of the Schrodinger equation. So this is how you construct the wave function. So first of all, remember this DFT wave function in fact is always an approximation. It depends on how many terms you include in your sum, right? Then in order to calculate the energy, at least in modern codes, the way that you calculate energy is not in fact by plugging this back into the Schrodinger equation and solving a equation. Instead of doing that, what you do is that you use this wave function and you write an energy functional and you use a variational method. In the variational method, again, you probably remember this from your quantum mechanics, you construct an energy functional. It's given as the kinetic energy and the potential energy for the wave function that you got from the augmented plane waves. Okay, and then you take this energy functional and you minimize it, or you you make it stationary with respect to the wave function, which means that you demand dE deep psi to be 0. That's a variational approximation in order to get the energies. And those energies are going to be an approximation of, they're going to be your band structure. But they are an approximation to the real band structure because your original wave function was truncated at some level. You had to, for example, you include 100 wave functions and then you stop. And then you start minimizing this energy functional. That's how you get the band structure from minimizing this functional. And the condition, in fact, eventually comes down. So this has to be dE deep psi, but psi itself is made of these coefficients, C coefficients, so you get dE dCk equals 0. And again, if you have, for example, if you include, let's say, n augmented plane waves into your wave function, you will come up with an n by n matrix equation. The roots of that matrix, so you get a determinant of that matrix, you put it to 0, the solution to that will be the energies. This is how you get the energies, and this is why you need computers to do it, because this can be 100 by 100 or 200 by 200 200 by 200 matrix equation. In fact, it's maybe a good point to pause and say, you see, there is a big push to make, to succeed in building quantum computers, right, to facilitate the quantum computations. In fact, probably the best peaceful use of quantum computers is really to do that, actually, is to do chemistry, in fact, to be able to understand the exact, so if we were not limited by computational power, we could do this exactly. We could include as many terms as we wanted and to get an exact solution for the behavior of a material. We cannot do it because we're limited in computational powers. If you, the next generation of scientists, if you in fact build a quantum computer, this would be probably the best use of quantum computers, because then you can truly come up with band structures, and those band structures are correct. They're not some approximation like what we have to deal with. Okay, here I show an example of this band structure with the augmented plane wave. This is done for iron, for copper, for zinc, and it's used, the method that is used here are augmented plane wave. The Muffin Tin Radii, usually the radius of Muffin Tin is taken to be less than half the nearest neighbor distance. So if I go from, say, this point, the center of this unit cell to the center of this unit cell, halfway through would be the maximum for the radius of the Muffin Tin. Usually it's even less than that. So in this case, for example, you see it's about maybe 30% or 40% of the nearest neighbor distance. That's the radius of Muffin Tin. And it actually determines the accuracy and the result of your DFT solution. So here you see it for iron with a BCC unit cell. This is the Brillouin zone of iron. For copper with an FCC unit cell, that's the Brillouin zone of the FCC unit cell. And for zinc with a hexagonal close packed, and that's the Brillouin zone of a hexagonal closed packed structure. Zinc specifically, if you look at zinc band structure, you see it is very much quadratic-like. It's very much like a k squared. Here is k squared, then here is k squared, here is k squared. It's actually exactly looks like a free electron behavior. And the reason why that is the case is because zinc is predominantly made of 4s2 orbitals. It has 3d10. The d shell is filled. That's the core level. It's completely filled, and you only have s electrons. And therefore, the solution will be almost like free electrons. Very similar to what I showed in one of the earlier slides, exactly like this. You see it's quadratic, and there's a little gap here. And that's exactly what you see in zinc. Now, here is a view on one of the programs that does this computation. This is the one my group uses, and I think many experimental groups use this. We're not really, I mean, I am an experimentalist, by the way, but we do a little bit of DFT computations.
I had a question about the augmented plane
Yes,
waves.
yes,
So are we
please.
using the augmented plane waves to define the waves for valence?
Absolutely correct. Yes, yes, absolutely correct. Yes, you use it to calculate the valence band structure. The core levels are separate. The core levels are completely, they are the solutions to atomic Schrodinger equation within their Muffin Tin Radius. However, in these, one of the things that these computational methods do, so this was the way actually, this was the way that it was done maybe a couple of decades ago. More recently, what's added to this technique is that because now we have computers, with computers you can write more sophisticated algorithms, and what you can do is that you can calculate the valence bands, you calculate the core levels, and there's something called a mixer, which is in fact the most computationally expensive part of these codes. It's the part that starts mixing the core levels and the valence bands, but this has to be done very carefully. You should not leak too much charge out of the Muffin Tin Radius, and so all of this you have to control when you're doing the calculations. You should constantly check these things. So you can calculate the band structure, but it may mean nothing at all. So it has to be carefully done. Okay, so here is the way it usually works. So there is some algorithm. So one of the things that, so for example, here you can see LAPW1. This is one of the steps. Sometimes they say LAPW1. This stands for localized augmented plane wave. And usually you start with a LAPW0. That's the very first iteration, and then you go to LAPW1. In this step, you start calculating the valence bands. You set the Muffin Tin Radius. You tell the program what you want your Muffin Tin Radius to be. You tell the program what is your convergence criteria for charge and for energy. And you do the first round of LAPW, or the augmented plane waves. Then you do something else called LAPW2. In the second LAPW is when the program, in the first part, it solves for the valence bands. The second part, it solves for the core levels. And after that, there is a mixer. This is where the core levels and the valence bands start to mix together. Okay? And then it feeds it into a convergence criterion. If it is yes, it stops. If it is no, it goes back to LAPW1, LAPW2 mixer. Usually these are the steps. LAPW0 for the very first computation, then you go LAPW1, calculate valence bands, LAPW2, calculate the core levels, mixer, mix them, convergence criteria test. If it's a yes, you stop. If it's a no, you go back to LAPW1. You iteratively keep doing this until you converge. The advantage of, I will show you maybe one other thing. JP, how much time do I? One, okay, so I will stop, okay, fine. I will show one last thing here, that just to see that some of the stuff that we talked about, this is exactly how the computations work, in fact. So here is the wave function, for example, okay? So as I told you, you need to sum over a number of these augmented plane waves. The augmented plane waves, they look like a free, sort of a plane wave multiplied by the augmentation part that looks like an atomic wave function. So this is the wiggly part, this is the plane wave part. But you always end this sum at some k max. And this k max, that's exactly where the approximation comes from. You see, the solution to the Schrodinger equation is all good, no problem. The thing is that when you construct the wave functions, you have to sum over a limited number of terms. And that is the computationally difficult or challenging part. You have to stop at some point this sum. And this sum, there are protocols to do to end it, and you decide where you end it. Within this code that we use, WinUK, there is a parameter called RK max, and what it is, it's a multiplication of R by K max. R is the radius of muffin tin, and you can take the radius of muffin tin, for example, to be half the distance between nearest neighbors. This is a very common parameter. You take the distance between neighboring unit cells, half of that would be the largest muffin tin radius that you can define. Okay, so then there is a table here, for example, that would tell you if the smallest atom in your calculation is one of these, you calculate this number for RK max. For example, let's say I'm using nitrogen, for example. And I'm looking at some nitride, for example. So I'm going to pick number 6. That means that R, which is half the distance between neighboring unit cells, times K max has to be 6. That means that K max has to be 12. That means that there will be 12 terms in this sum. Okay? And that determines what is how much computational computational power I put in this. This RK max is also known as the basis size parameter. So again, in every DFT paper, you will see these things that they say what is the RK max, they say what is the basis size, and usually the CPU time scales with the number of plane waves to the power of 3. So for example, if you increase the RK max only by 10%, okay, the CPU time that you're going to use will double. So very soon your computational people will start yelling at you because you end up using too much CPU time and they have to cut you at some point. So sometimes the accuracy of your DFT is determined by when the computer people cut you off. At some point they just kick you out. Okay, I had more to talk about, but I think this is maybe a good place to stop. So we covered the basics of band structure calculations. We see the goal is to calculate the valence band in metals, the energy of valence band as a function of momentum. And you see that the calculation eventually boils down to calculating the solution to Schrodinger equation, but for a lattice. And you can see that a lot of things you learn in quantum 2, say in solving the Schrodinger equation for hydrogen atom, a lot of these methods, for example, the cellular method is exactly that, except that instead of an atom, you use a unit cell. And you impose your boundary conditions to a unit cell. And you also saw that what are the factors that limit the accuracy of these calculations is the size. The basis size is probably the most important factor, and the number of boundary conditions that you have to impose on your band structure. There is also a convergence criterion that you have to impose and stop your calculation at some point. And most importantly, eventually, these calculations will give you some band structure. This is how it looks like. It's energy as a function of momentum. And here, I'm showing the calculation for magnesium oxide. It's a very simple material with rock salt structure. And the only difference, you see the band structures are similar between these two plots. The only difference between these two plots is that they use different potential. Both of them are using muffin tin potential, but the kind of muffin tin is different between these two. One of them is a muffin. This is the most famous way of, this is the most commonly or most widely used muffin tin potential. After Purdue, Burke, and Erzenhoff, PBE potential, you will see this probably a lot in any DFT paper that you read. But lately there are efforts to come up with new functionals that work better for insulators specifically. This one is called a modified Beck-Johnson. So for example, the PBE works better for metals. MBJ works better for insulators. For example, in these two computations, they're both done by augmented plane wave. They have the same convergence criterion, and the only difference between them, they're both within the muffin tin radius approach. The only difference is that the potential that's in the muffin tin is different. And you can see that the band gap is different between the two. That's the main difference between them. This is a band gap, and this is another band gap. Okay, and the PBE underestimates the band gap. In fact, this calculation is better for magnesium oxide. It's an insulator. The modified Beck-Johnson, which was introduced, I think, in late 90s or maybe early 2000s, is a much better potential to calculate for insulators. And here you can see how that band gap is. You see the convergence criteria here. So this is the first iteration of the calculation. It gives a band gap of 4.5 electron volts. Then in the second iteration, almost immediately the program fixes it, goes to about 7. The band gap in this material is about 7 electron volt. And then it kind of starts playing with it. It's going the wrong direction. It goes back up the right direction, keeps going until say the n energy at n minus energy gap at n minus 1 is less than, let's say, 0.0001 Rydberg. And at that point, the program stops and tells you that that's my solution. And you get the correct band structure. I guess here I showed a complete example of all of it. I apologize if it was a little bit maybe too much, but I hope it helped you to at least get a flavor of the DFT calculations. Thanks for your patience. If any questions, please ask me. And I'll be around also the whole day. So I'll be, any questions, just come over and talk to me. I'll be happy. Yes, absolutely. Absolutely. Yeah. All of it will be posted, and I'm around the whole day. Come and talk to me.
So just a few minutes for questions. We're not too late. Questions? No one's going to ask about student potential?
Yeah.
Just a question. So eventually this will, somehow all of this set will exhibit anti-symmetric?
Yes, of course, yes. The wave function, exactly, it has to be anti-symmetrized, yeah. So this is a part of, again, your algorithm. So your algorithm will calculate the valence electrons, will calculate the core electrons, will anti-symmetrize the wave function, will mix, in fact, the core and valence, will anti-symmetrize the wave functions, calculates the energy, looks at the criteria, and goes to the next iteration. Absolutely. Yes?
At the very beginning, you showed two calculations for vanadium. So one was, I guess, 4s233, and the other one was 4s134. And so the 3D3, or 3D4 rather, had all the levels shifted down quite a lot in terms of energy. And is predicting which is correct as simple as that the energies are lower?
Yeah, I mean, in a sense, let me actually show that band structure so we talk on that slide. Oh, no, sorry. Here. Yeah, so this one is done with 3D3 4s2. This one is done with 3D4 4s1. And of course, you can see that the results between these two are different. One of the things that you notice between these two is that somewhat the energy scales of some of the bands, especially these bands, are higher than these bands, right? And some of these bands, the reason why these energies are, so your question is, how do we decide which calculation is better and which one is?
Well, I'm just assuming that since it's vanadium and it has an odd number of electrons, it's going to be half filled.
Yes.
So if I was going to half fill both of those, it looks like the total energy on the left would be lower than the total energy on the right.
Right.
Simple.
Yes, yeah, absolutely. That is absolutely correct. But eventually, so how you eventually decide what is right or what is wrong, in these cases, is there are a few things that you can do. So the answer is always the experiments will tell you what is right or what is wrong, right? So for example, today you can do ARPES experiments, and you can look at the dispersion of bands. You will visualize these bands. But even if these ARPES is not available, you can see that, for example, the curvature of these bands are different from each other, right? So wherever you put your Fermi level, the curvature of the bands are different. When the curvatures are different, that means that the band velocities are different. Then based on the band velocities, you can calculate, for example, the electron mobility. And then you can measure the resistivity and do some, like that way you can, for example, tell whether this material has a higher mobility or lower mobility. Or, for example, based on the density of states. So here you can again sum on the density of states. For example, you see this band here is flatter, right? And let's say your Fermi surface goes through here, okay? So this band is flatter. That means that it will give you a very large density of states. Then you measure, say, specific heat. And if you see a large specific heat corresponding to a large density of state, you would know that this one is better than that one. So even without ARPES, you can still kind of tell which one is correct, which one is not correct. Yes. Next, you were saying something?
I was just going to say, could the truth lie somewhere in between?
Oh, between these two, I actually don't know exactly. I would say that probably with vanadium, if I would make a guess, probably this one is more correct. But I'm not sure if my answer is correct right now.
John,
Well, related to that,
Yes.
the choice of valence.
Yes, yes, that's true.
The DFT will sort of force the solution on one valence to experiment, I'd say.
That's true. However, this one specifically, because this is just vanadium metal at this, right? So this only is based on the orbital sort of distribution of electrons. But if you're in a compound, of course, then for example, you can have vanadium 2+, vanadium 3+. Yes, and all of that also comes from DFT. In fact, as Jason was talking in his talk, that sometimes you may get, let's say, the structure correctly or the structural transition correctly. In fact, I must say that sort of connecting to your talk, DFT calculations are done not just for electronic structure, but for the crystal structure. And in fact, the crystal structure part of it is much more straightforward and usually much more correct, which is what you see usually in experiments. So you do X-rays under pressure, as Jason does, and DFT does a good job in capturing the correct structure. And the way it does is that it minimizes the potential between atoms, and that's a fairly straightforward calculation. The part that's tricky is to get the valence, as you mentioned correctly, in a compound, or to get the band structure correctly. It's much more complicated, and that's where DFT can easily fail. Yeah.
So,
yes.
It seems like with the electronic interactions, we sort of get them away in this like or I guess you do something with that. But what happens when you have like how is there a way to handle like more like exotic interactions, like if you have like magnetic interactions, like could this predict like something like instability to antiferromagnetism or something like a convergent bound state like an arc KY or something?
Absolutely, yeah. So let me it's a very good question. Let me respond in two parts. The first part, should I make it quick? Okay. Okay, two quick parts. The first part, I tell you, if you have no magnetism, the way I interpret your question is that why does the free electron approximation work at all, right? And the reason why it works is that you can take this, let's take this psi and write it in two parts. One part is the plane wave, and the other part is an atomic-like wave function, like augmented plane wave. In fact, the method that I'm describing is called the orthogonal plane wave, the OPW instead of APW. So if you do that, what you get here, you see, this is where the potential comes in, and you're asking about the effect of potential. If you have only an e to the ik dot r, okay, the e to the I dot r and e to the I minus ik dot r, they cancel each other in this term, right? And you end up by an integral over potential over the entire unit cell. And if you assume the material to be centrosymmetric, that integral will be 0. So in fact, the potential itself kind of cancels itself almost. So for the plane wave, the only part where the potential will survive is in the next term, the part that looks like atomic wave function. But remember that the part that looks like atomic wave function, that part is very wiggly. It kind of goes from plus to minus, plus to minus, plus to minus. And therefore, you're multiplying this wiggly term by a u and integrating it. The contribution will be small, right? Because you have some potential, but you're multiplying by something that oscillates very fast. And you're integrating. So it automatically will be, the contribution from this term automatically will be very small. That is why, to begin with, that's kind of the deep reason why the free electron approximation works so well. Now, the next point on your question is, then where does the other things come in, other potentials, such as magnetic potential, where do, for example, if you have now spin in there and magnetic interactions, where do they come from? So they require the only part that you can include in U is electron-electron interactions, because it's like a Coulomb potential, like electron-ion interaction. If you have magnetic interactions, you have to specifically add additional terms to your U. And that means that your computation will be a more advanced computation. You have to include spin interactions in your computation. So your U will be a U that's a charge part, that's a sum of periodic potential of the lattice plus the electron-electron interactions, but there will be another term, which is the spin-spin interaction. And that part, in order to calculate it in your protocols, you have to then add the spin part to it. For example, here For example, here you do lap W0, you do lap W1, you do lap W2. You do not go directly to the, you can go to the mixer, but after that you have other steps. You have to then, for example, add the spin polarized calculation. So the other part of the U which has spin in it, it will kick in. So you will do the spin polarized calculation. So there is a lap WS and there will be a lap WSO. Then you will do spin calculation, you do spin orbit calculation. So those terms will be added to your algorithm. It's a separate, the way you do is that you first do a normal DFT calculation with only lap W1, lap W2 and mixer. You converge that as if there is no magnetism. Then you start from that starting point and add the magnetic interaction as an additional term, and you redo your calculation. Usually this is much faster than including everything out front. And you have to redo that calculation. That U was not included in anything I showed today. It's a separate term. We can talk again more if you want after this.
Okay, lots of questions, but unfortunately we have to get to our
Sure.
module.
Sure, absolutely. All right, thank you.